Hello, welcome to my recording for my homework 6 for digital systems. So, as you can see, our first part to the homework was to create an FSM and an ALU and integrate them together to make the ALU do operations. And in this case, the ALU's output never integrated with the FSM. So, in that code, my ALU does 4 different operations. It can add, do bitwise ANDing, bitwise ORing, or bitwise NANDing. And that operation is determined by my FSM, which is the code right here. So I have a clock and a reset signal, as well as an output signal. So that tells what the ALU should do. My sequential logic statements go as such that if on the rising clock edge, the current state is equal to the next state. If reset's 1, however, the current state is the base state, which is 0, 0. However, if the current state is the next state, or the current state currently changes, the next state is 0, 1, the output 0, 0, so it adds my A and B. When it's in state 0, 1, it transitions to 1, 0, and then it sends out an AND signal. 1, 0 transitions to 1, 1, sends out a 1, 0 signal, so it ORs them together. And the final one goes back to state 1, but sends out a NAND signal. So if we look at the top level, this is where all the components are added together. So I have a component of my ALU and of my FSM, and I integrate them together with a signal select. So that way the FSM can determine what the ALU should do. And in my test bench, I show, first I create a count signal. So that way it can iterate, there's a count and it iterates the signals and changes them, like clock, so it changes every other bit, and it generally helps make sure that the process and the run is singular, and it makes it a lot easier to visually see this. I have my component of the top module, which has both my ALU and FSM in it already, and any inputs that need to go into that system, such as the clock and reset, A and B, and the output will come out so we can see it. So I set my A and B to 10 and 5 respectively, so I know the operations happened correctly. And then I assert so I can see the signals. Alright, so I've already run the simulation, and as you can see, before my state's undefined, but on the very first clock edge, it transitions to 0, 1, so it's ANDing them together. Excuse me. On the very first clock edge, you can see, sorry for the slow speed, computer really hates Model Sim for some reason. Not zoom full, zoom in. Alright, here we go, sorry about that. So here, my clock is in state 0, 0, so it's adding them together, and here it transitions to its next state and it ANDs them together. Then once again it ORs them, but reset causes it to go back to 0, 0, then it ANDs and ORs, it ORs and NANDs them after that. So Welcome back. So we just concluded on our part 1 for our homework 6 for our ALU and FSM combination. So in part 2 we are actually combining the FSM and ALU with the output of the ALU, determining what the FSM does next. So I've already went ahead and loaded the signal and everything. So currently I am on the FSM code. So here's how it works. I have an enable signal, a clock, and a reset, a 4-bit unsigned number to receive the output of the ALU into my system, and an output of 2 bits to tell the ALU what to do next. So, like normal, clock and reset. If reset's 1, state's automatically 0, 0. Else, if it's a clock event, the next state will determine what the current state is equal to the next state. Okay? So, in the next process, if enable is 1, then the process will check the current state to perform the operation to check if something's even or odd. If it's odd, it will OR them together. If it's even, it will AND them together. Otherwise, for every other state case, it will do addition. Else, if enable's not on, the output to the ALU is straight addition, the next state's 1, 0, but it won't change but it will just stay where it is and continuously come back and be assigned 1, 0 until the next clock edge occurs. So the top of our units together is exactly the same as the previous one with a few modifications. As you can see, I have 2 different signals. One so I can see the output of the top, and as well as what state we're in. Beyond that, there's no other differences between this one and the other test one. But test 2 as well, pretty much the same code, just 2 additional signals so I can see what's going on. And clock and enable are assigned to a counter variable, so it will iterate through when we run it. I think that's pretty much it. Our ALU code remains the same: 0, 0 addition, bitwise AND, or NAND. Alright, so running our top module in the test bench gives us this result. So as you can see on the first clock edge, we're assigned 0, 0 as our current state. As you can see from this line right here, 2H0, so my current state is 0, 0, and my output is the addition of 1, 0, 1, 0 and 0, 1, 0, 1, which should be FF1111 or F in hex, which is correct. So as you can also see, enable is not on, so it will continuously hold this state until enable changes, but not immediately when enable changes until the next clock cycle. So right here on this clock edge, it will shift to state 1, 0, 0, 1, and then it will OR them together, AND them together. And then on the next clock edge, it's 1, 0, and then it's going to OR them together. And then when enable's off, it goes back to 0, 0, keeping the states. So that completes my explanation of my ALU. And to reiterate, my condition is that if the operation is only performed if enable is 1. Else the operation is not performed, it doesn't change states. It just basically holds out at 0, 0, and just adds the 2 numbers together.